Hello, I'm Megan Beckelay, Program Director for the Electrical and Computer Engineering Department Heads Association and moderator for this webinar on AI in Education with Jetson Nano, brought to you by NVIDIA and Duckietown. Before introducing our speakers, I have a quick housekeeping announcement. We will be accepting questions throughout the presentation, which you can submit using the Q&A text box. To access the Q&A box, simply click on the Q&A icon at the bottom of the screen. Now it's my pleasure to introduce our speakers today, beginning with Dustin Franklin, developer evangelist on the Jetson team at NVIDIA. With a background in robotics and embedded systems, Dustin enjoys helping in the community and working on projects with Jetson. You can find him on the NVIDIA developer forums and GitHub. Joining Dustin today, we have Jacopo Tani. Jacopo is a senior research scientist at ETH Zurich in the Frizzoli Laboratory of the Institute of Dynamic Systems and Control, Department of Mechanical and Process Engineering, and co-founder, president, and CEO of Duckietown. With that, I will hand it off to you, Dustin, to get us started.
Hello, everyone. Thanks, Megan. Appreciate it. Thanks, everyone, for joining us today. So this webinar, we're basically going to talk about AI and education, specifically hands-on devices and how you can get students started, everyone from undergraduate to research or even at the high school level. So first, we're going to briefly start by introducing the tiny devices that we're doing this on. These are called the Jetsons, and then get into all of the course materials and labs and tutorials that we have available. And then Jacopo is going to come on as our guest speaker from the Duckietown organization and talk to you about what they're doing with their massively online course. So with that, let's thought we would get started with a little preface about why we're all here and interested in this topic. As I'm sure, as you all have seen in the past years, there's been huge growth in this field, really prompted by the rise of machine learning and deep learning back as far as 2012. And very interestingly, from this chart here, this is from this LinkedIn 2020 jobs report. These top three positions, the AI specialist, robotics engineer, and data scientist, these are all directly pertinent to this field and what we're going to be talking about here today. So there's huge opportunities out there for students who graduate and want to get into this exciting field, everything from self-driving cars to robotics and healthcare, AI at the edge, not to mention all of the cloud-based applications for AI. So it's really exciting to get into. I really love working in this field personally and supporting the community, and wholeheartedly recommend anybody who's graduating today to give this a really good look as an area to go into. So kind of on the flip side of the jobs and opportunities that are available out there, on the back end of that, we see a lot of deployments of robots and smart devices being put out there into production and into the field using these intelligent computers and AI-powered machines. Everything from precision agriculture and smart tractors to healthcare devices. They're very popular in manufacturing, taking the manufacturing arms to a next level of autonomy. And these robots are very popular in logistics and warehouse environments as well, and last mile delivery. And interestingly enough, I've also seen these robots start to show up in my grocery store here in town. I was walking around the one day and saw one of these retail restocking robots that had a little Jetson inside of it scanning the shelves. And basically all this is made possible by this increased horsepower these devices have at the edge to be able to run these complicated deep neural networks and perform a level of autonomy on board that they weren't capable of doing before. And it's very similar to self-driving car technology, just scaled down to much lower power processors and a much smaller footprint. So this is just a sampling of a lot of the professionally developed and deployed applications and platforms that are out there. But in the Jetson community, there's a lot of open source projects and applications, and there's a very vibrant developer scene going on there where folks are making devices for their house or small little robot kits. everything from healthcare devices, or we've seen a lot of COVID-related ones where people are making mass scanner devices or smart social distancing applications. So there's a very active developer community built around here, and we post some of the best projects to this page. We can go and then these are all open source on GitHub or other open source platforms, and enable other folks to go and build their own AI projects and get started with themselves. So it's really great to be part of a community like this. So this is the Jetson device I keep talking about that is actually behind the scenes running all of this stuff. This is the latest product that we've released earlier this fall called the Jetson Nano 2 gigabyte developer kit. And it's the least expensive and smallest product that NVIDIA's ever made, actually. And it's fully intended for AI in education. So this was really the reason we created this. Back in 2019, we launched the original Jetson Nano, the 4 gigabyte model, that was priced at $99. And then we scaled this one down to $59 to really bring it in the hands of everyone, on all students, anybody who wants to get started with AI and machine learning. And the cool thing about this is you can run TensorFlow or PyTorch or all of the machine learning frameworks on this, or ROS, or a whole lot of other software that might need to be on a bigger computer, but you can take the low cost of this and small size, weight, and power and fit it into a small handheld device or a little robot that you're making. But it still has really great performance, more than most people's laptop or PC even. And it runs the full NVIDIA suite of software, the CUDA stack and everything. So it's like just having one of the larger discrete GPUs in a PC or in a server or cloud instance, and be able to take that same software and scale it down into this small, low cost, low power device. So here are the specs of this dev kit. It has a bunch of USB ports, HDMI, Ethernet, comes with Wi-Fi on it. So it's basically just a small little handheld computer, not unlike a Raspberry Pi, but that has a lot more compute horsepower on board because of that NVIDIA GPU that's integrated into the chip. Now, I will mention there's many other Jetsons in the Jetson family, and they're all compatible with each other. They all run the same software, and that's really nice from a deployment perspective if you're doing embedded projects or embedded designs, because you can really pick and choose which Jetson product fits for your size, weight, and power and performance requirements. So on the lowest end, there's the Nano, 5 to 10 watts, half a gigaflop, or I'm sorry, half a teraflop of performance. And on the high end, there's the AGX Xavier, which is up to 30 watts and 32 teraops of performance. In the middle is this Jetson Xavier NX, which is small like the Nano, but has up to 21 teraops of performance. And that device is really the nexus of both the small form factor of the Nano and the big performance of the AGX Xavier. So if you're a researcher looking to do like pretty high-end stuff, you might look to the Xavier NX. If you're teaching a course or want a lot of these devices for folks to get started with, making small autonomous robots like the Duckietown, then the Jetson Nano we've seen is a really great fit for folks to get started with. And a lot of devices in the field, smart cameras, smart other devices, deploy the Nano as well into production. So those were the modules. So these little modules actually go into a carrier board that then breaks out all the ports. And we bundle these and call it the dev kit. So it essentially comes with everything you need to get started with. As mentioned, there's the Nano 2 gigabyte, which is the big one in the education market. And then the full Nano, there's the TX2, the Xavier NX, and the AGX Xavier. So all of the Jetson modules, which are intended for commercial deployment, those all come with the dev kit option as well for ease of use and getting started with. And there's a lot of ecosystem and third-party carriers that are made for these, so folks can customize the I/O and deploy it directly into a device or plug it straight in. So I mentioned that the Jetson devices all run the same NVIDIA software stack that you would see on a PC or in the server. On Jetson, we call this Jetpack. It basically comes with CUDA and cuDNN and TensorRT and all of the NVIDIA libraries that really accelerate these machine learning frameworks under the covers. So most folks that are using PyTorch or MXNet or TensorFlow, they will just flip a switch and turn on GPU acceleration. That's because they have cuDNN and CUDA toolkit and all of those drivers installed there from NVIDIA, which actually executes the stuff on the GPU. And the nice thing is all those same libraries are available on the Jetson, so you can run all that same code that you would have on a PC and just scale it down to deploy into this embedded device, which makes it really nice for getting started with. The environment's not any different than what you would see on a PC other than being on an ARM CPU instead of an x86. So I mentioned the performance of the Nano. It's rated for half a teraflop of performance, and both the Nano 4 GB and the 2 GB have the exact same performance to them. The chip specs are the same CPU, GPU, just less memory for the cost reduction. But we can see here you can deploy lots of high-end models that you might only see on higher end systems, but be able to run them on these small embedded devices because of that GPU acceleration. So probably the most popular are these object detection models like SSD MobileNet or Tiny YOLO or the full YOLO. Even the open pose model is very popular as well for pose estimation. And this is just a small sampling of these benchmarks that are some of the most popular models out there in the community. The truth is you can practically run any model that you want to take or find out there, run it through your framework of choice, and be able to, deploy it to your Jetson. And these benchmarks are all open source at that URL down there, so you can take those and run them on other devices as well. This is just to get a feel for what type of performance that you can expect. And in general, we see folks like are always hooking these up to cameras. The hands-on aspect of Jetson's what really separates it from just learning in the cloud or whatnot, processing static video files, because it's really great to be able to actually play with these models in a real-time environment and train your model from a collected data set and stand in front of it, see how it reacts, and that kind of informs you of maybe you need to collect more data or different types of orientations of your objects, things like that. So can't be understated enough the importance of being able to actually play with these models from a real-time camera feed. So I've been mentioning all these frameworks that you can run on Jetson. You can practically compile and run any of these popular machine learning frameworks because the GPU acceleration has already been integrated into them for a long time now. There are some that we very explicitly support that are very popular, like the ones shown here. So we work with a lot of folks to make sure that these are all compiling and release the pre-built Python installers for these and Docker containers so that you can get these up and running super quick without even having to build them yourself. So far and away, the most popular ones are PyTorch and TensorFlow, ROS, and Docker. So those get a lot of use on Jetson because they're popular in the broader machine learning community as well. And these run the full versions of these frameworks. It's not like TensorFlow Lite, for example. You can just take TensorFlow code off the web and run it straight on your Jetson. Even if you're doing training, we have lots of tutorials that are actually training models on the Jetson. Obviously, in big models, big data sets, you would be wanting to use a much larger system for that. But for learning purposes, it's very effective. Take a data set of 10,000 images, a few gigabytes, and actually be able to train it right there so all of the students can go through that and do it as well. So I mentioned the containers. We've been into this for a few years now. Obviously, they're extremely popular in the cloud, and even on PCs and servers, because the truth is a lot about these machine learning frameworks, they're very complicated to install. They have lots of dependencies. A lot of the machine learning projects have lots of libraries that they're dependent on, and the Docker containers are a very common delivery mechanism of machine learning projects out there. And we've seen this same paradigm now shift to the edge, and be able to run containers just the same way that you would on, a cloud instance or whatnot. And it has a lot of benefits to it, most of which is being able to totally bundle and deploy that application. So if you want to set up your course curriculum or whatnot, you're making a lab for all the students to do, it's very easy just to make a Docker container for them, and then they can pull that and have the environment for doing their programming assignment or whatnot in there, as opposed to spending several hours trying to install everything ad hoc, because these Docker files essentially script all of that in there for you. And it's very easy. Let's say you have, 15 or 20 of these devices that you're teaching a class with. You can manage those all remotely, push containers, start them using orchestration services like Kubernetes and whatnot. And we see a lot of this used in production on Jetson and Edge devices as well, because folks have large fleets of these for IoT and things like that. And they're managing all of their apps through Docker, and makes it very, very easy to deploy at mass scale out to the edge. And for those of you who haven't used Docker or these containers before, because even a few years ago, I hadn't myself, but I've come to be a big believer in it, because like when I have to rebuild all of my code, all of my examples, basically just hit a button and, it does everything for me. And the performance is exactly identical to what it would be if it was outside Docker, because it's not running in a virtual machine. It is basically just isolated Linux processes through what's called C groups. So it is still executing totally natively on your device. It's just using a bunch of file system tricks, essentially, to isolate all of these containers and processes over from each other for security. So unlike virtual machines, there's no performance hit whatsoever to deploying these. Okay, so now we're going to start to transition into what actual learning resources are available, the course contents, the tutorials, and stuff that we've made, not only for teaching, but in the broader community as well. We've done a lot to enable folks to get started learning machine learning and deep learning and all that stuff. Even a few years ago, I'd, not done that myself either. And it was much more difficult circa 2015. Seemed like you needed a PhD or some postdoc researcher to understand what all of these folks were doing. But since then, it's become really a lot more approachable and more democratized and easier. So we've put some stuff out there. The community has made a lot of stuff as well that really lowers the bar of entry for folks that just want to get started and figure out what it's all about and how they do it for themselves. So there's a bunch of robot kits and courses that are already available out there that you can go and visit. Duckietown is one of them that Jacopo is going to speak to shortly. But there's other ones as well, like MIT has this long-running race car course, in addition to the UPenn F1 10th circuit. These they're like RC race cars that have been modified to be fully autonomous. And they're very popular with undergraduate students because there's a competitive aspect in the course to them, where the teams are competing to get the fastest lap times. Some of them have even started doing Grand Prix mode, where there's like multiple of these on the track at the same time. So there's full courses out there that are built around this, and they're also popular because the self-driving car engineer track for students is popular to get into. And these are like a little self-driving car. They have Ackerman steering, and they have LiDARs and stereo cameras and the full sensor suite, essentially, just in a scaled down, low cost version. So we see these type of platforms being pretty popular. They're slightly on the higher end than what you might see from the Duckietown or the JetBot in terms of cost. So in general, folks will start with a Duckietown-like platform or the JetBot-like platform that we'll talk about shortly, just as like your first exposure to robotics and autonomous algorithms and deep learning and things like that. And then you can go to these higher speed, higher performance platforms like these race cars. I think some can do up to like 40 miles per hour. They can be very fast. And then there's an additional one from the University of Oregon called the Musher. It's basically an even more souped up quasi off-road platform, and there's a full course built around that as well. In addition, along with the launch of the Nano 2 GB a couple months ago, NVIDIA has actually launched our AI certification program, which we'll talk about next. And essentially, you can get started, follow our tutorials, and then submit a project showing off AI and making your own deep learning model or applying it in some way, and then receive a certification for that. Um, the course is called the Jetson AI Fundamentals course, and there's actually two certification tracks within it. One is called the Jetson AI Specialist. That's for folks that are just students or hobbyists, or anybody can get that. And we've seen professionals do it. And then there's the Jetson AI Ambassador. That's for educators specifically. So if you're interested in teaching Jetson related courses, teaching this content to your students, you can apply for this Jetson AI Ambassador certification, and there's a bunch of perks to that. For example, you can qualify for these seeding grants that you can get Jetson Nano 2 GB for your class, other things from the Deep Learning Institute. Deep Learning Institute is NVIDIA's kind of education group, and they run a bunch of these ambassador programs, and we work very closely with those folks in the education community to help enable them, give them trainings that they can in turn give their students and things like that. So the Jetson AI certifications, basically you take this, what we call the fundamentals course. It's made up of 3 labs, and it takes students a few days to run through these. There's the Getting Started with AI on Jetson Nano lab. That's like meant as the very first exposure to machine learning. You don't even need to know Linux or anything to do that. Basically, it just comes up in this Jupyter lab environment, and you start collecting your data sets, playing around with the camera, training the models, just to really learn about that machine learning workflow. And then next is the Hello AI world, where you're actually making your own AI projects and coding some Python and doing more hands-on training stuff. And then finally, the JetBot, where you're building a physical robot and training it to navigate around autonomously without running into stuff. So we made a bunch of YouTube walkthrough videos for all of this for the launch of this certification program and the AI fundamentals course. So if you're interested in what all of this stuff is about, I recommend checking out these YouTube videos, because you can see exactly what we're doing as we go through this ourselves. And every step is there. I did the Hello AI World ones. My other colleagues from NVIDIA filmed the other ones, and you can see every step as we go through it together, and it's very good for guiding students through it as well, so they don't just need to read the documentation. So all of this is backed by extensive documentation, either on GitHub or the Deep Learning Institute site, and all of this is totally free content. The certifications are totally free to get. Okay, so just to dive in a little bit about each of these 3 different labs, let's say each lab is like an 8-hour lab. So you can basically do these all in a week. And then if your students want to get certified or you want to get certified, you can make your own project and then basically apply, and we'll get back to you with your certification certificate, essentially. So the first one, that's Getting Started with AI on Jetson Nano, it's basically a bunch of Jupyter notebooks that you can run headlessly from your Nano, and you don't even need a display or anything for your Jetson. You just like plug it in to your PC and it establishes a virtual networking connection. You also plug in a webcam to it, to the Nano, and then fire up these Jupyter Lab server. This course comes as its own Docker container. In fact, all of these labs that we've talked about, the Getting Started with AI and Jetson Nano, the Hello AI World, the JetBot, those all have their own Docker containers, which makes it very easy for students and anyone to get started with them, because you just run this script that pulls the container and boom, there's instantly the whole environment for you. So first timers don't need to learn about installing TensorFlow or PyTorch or Jupyter Lab. They can just instantly go in and use these. And what we've done is made these interactive widgets inside of the Jupyter Lab notebooks, where folks can basically point and click to capture data, to kick off training, and then test the inference. So it comes with a couple different projects to do. One is to train a image classifier that detects if your thumbs up or thumbs are down, and then you're kind of prompted to expand that into other ideas. The code is there, and we show you how. So if you want to make additional classes, let's say you want to train it again to recognize like sign language, or detect how many fingers you're holding up, or whatever you want to do with classification. A real cool part about these AI projects is not only learning about the the workflows and how you actually train this stuff, but also getting folks in the mentality of thinking, what can I actually apply this to, and the novel applications of it. And that's kind of a whole other realm to this that we help to inspire people with. And those community projects are very good for that too, because there's a bunch of shared capabilities: the classification, regression, detection, segmentation, but really endless possibilities for what you can apply that to, because you can just retrain those models on new data. So then, yeah, the second notebook in this is an image regression one, where basically you are finding different facial features like your nose, your eyes, and you basically just collect data and annotate it by clicking on it, and then it trains quickly, and then you can see the live video feed, and it displays little circles over the different facial features that you trained it on. And this is all interactive training. It all happens right there on the Jetson. In general, it just takes like a minute or two to train it. We found that you can train these with as little as 50 or 100 images just in this test scenario. So these aren't extremely robust models, but they do work to highlight the workflow. And for somebody just playing around in front of a webcam, they actually work really well. Okay, so the Hello AI World, it kind of builds on that first lab. And this one, you actually get to do, Python coding. You're making your own applications. It also supports C++ if folks prefer. But essentially, it takes image recognition, object detection, semantic segmentation, in addition to another few other machine learning capabilities, and then enables you to go off and build your own applications out of that. It comes as a library that's extensively documented, so that you can basically take that and build your own little Python or C++ apps out of, and has a bunch of examples in there too. And it also comes with all the guides for retraining all of those models in there, and also has interactive data collection, training tools, and things like that. So you can see here's a couple examples of things that you can do with it, and check out those YouTube videos for walkthroughs of actually going through this. And we see a lot of folks will go off and make their own projects out of this, because it's very easy to integrate with other code and into actual devices. Okay, so that brings us to the JetBot, which kind of takes all the previous learnings that we've done and it applies it to a real physical robot that does object detection, it does object following, it does obstacle avoidance, and road following or lane following, which is very popular. So generally what folks do is they'll tape down a little road on their floor, or make like a little Lego city, and train the JetBot to roam and navigate around that without running into obstacles. And this is also programmed very similar to the Getting Started with AI on Jetson Nano course, and everything is done through IPython notebooks over Wi-Fi. So you're interfacing with the JetBot from a laptop or PC, and open up this Jupyter Lab terminal, do all the trainings interactively, very similar to the Getting Started with AI and Jetson Nano course, where you're basically just point and clicking where you want the JetBot to drive initially. It trains that model, and then you get to experiment with it around when it's actually running for itself autonomously using these classification and regression-based deep learning models. And all these kits are fully open source, so you can go in there, and folks have made all new types of autonomous functions for these, which is really cool to see. So here's just a quick video of the JetBot
So over
in
here we
action.
have Jetbot, which is an open source robot that we built using Jetson Nano. And the idea behind Jetbot was to give people that wanted to start with AI, or maybe AI with Jetson Nano, a platform that they could just get up and running right away. You buy the components of the robot. We have everything on GitHub, so it's super easy to get started. It's all done in Jupyter notebooks. So we have like basic examples from just controlling from your web browser in Python. It's super easy to do. To more complicated examples like using AI for avoiding collisions. And then we go all the way to road following to have like kind of an autonomous car navigating a Lego city. So that's the basic idea, is that you can start with this platform. It's all open source, the hardware, the software, and then you can take what you learned, you can take the components even, and you could build something new, and who knows what that would be. It would be kind of up to you.
So JetBot started as a 3D printed open source platform. If you wanted to make it, you would get all these components off of Amazon or Robot Shop or Mouser, wherever, and 3D print your chassis, put it all together, and all the software and stuff, just came from the GitHub. But what we've seen is a lot of suppliers in the community, in addition to Duckietown, have actually come out with off-the-shelf kits of this, which make it very easy to assemble and purchase so that you're not individually sourcing all these components. So all these examples here, there's many different JetBot variations now that you can use, and all of these are able to run the shared JetBot software, and all of them have a very similar capabilities to them. So the Duckietown robot, Jacopo is here to talk about in the course that they're putting together and running. So with that, I am going to transfer it over to you. And let me stop sharing here.
Thank you very much, Dustin, for this nice, interesting overview of all the scenario of the NVIDIA Jetson boards and their various applications. So let me start by sharing my screen. So yes, I am Jacopo Tani. I'm a senior researcher at the Swiss Federal Institute of Technology in Zurich. And today I'm going to talk to you about Duckietown, which is an education and research platform that is fundamentally designed to provide robotics and AI learning experiences that are accessible, are fun, but most importantly are state of the art. And this is how it all started. If I manage to change slide. So this was 4 years ago now when we started building this platform at MIT to teach a course in self-driving cars in a way that was more hands-on, different from the usual go to the blackboard, do all the theory, run some simulations. The class was built by a number of PhD students and postdocs. It was the first iteration of the class had literally more staff than students, quite at a rate, nearly at a ratio 2-to-1. Then all these postdocs started migrating around the world, bringing Duckietown with them. And already in 2017, we started seeing Duckietown being used for research and for education in universities on several continents. From 2018, we started losing track fundamentally of how many people were using Duckietown. We were getting so many requests for various robot clubs, professors, researchers around the world that wanted to join the community and start building their small cities with their fleet of self-driving cars, that we wanted to make the whole process easier. So we did a Kickstarter and we created a pipeline to basically allow to delivery of the Duckietown hardware in a very standardized and quality controlled way internationally with one click. In 2018, we even ran our first edition of the AI Driving Olympics, or AI Do, which is a scientific competition that we run since then biannually at ICRA and the NeurIPS, the finals. And basically, we'll talk more about it later, but it's a provocation. AI Do, can AI actually do anything in the real world, right? We're trying to collect from the broader community solutions to various challenges of increasing complexity and trying to compare the various machine learning solutions to typical traditional approaches to robotics to see if the embodied AI system works in non-trivial, let's say, scenarios. Today, we have over 90 universities and various companies and research labs around the world that use Duckietown. And we are at the 5th edition of the AI Driving Olympics, that the finals of which are actually going to be running at NeurIPS on Saturday. And the next year, as Dustin previously mentioned, we are going to be launching a massive open online course on edX. It's a international collaboration led by ETH Zurich and together with a number of university partners, including the University of Montreal and the Toyota Technological Institute at Chicago, and the support of course, edX and NVIDIA. This course is going to be it's going to the best of our knowledge, it's the first robotics and AI remote learning massive online open course that has hands-on experience with self-driving cars. So every student at home can receive a small little city, so a robot, an NVIDIA-powered robot, and a little urban environment, and follow along with all the various classes. So the Duckietown project was born, as I mentioned before, for educational reasons, but really it was driven even by a research purpose. In our lab, we do lots of mobility research, and we were really missing a link between doing everything in simulation, testing autonomous mobility on demand systems and simulations, so say control systems for fleets of self-driving cars. And there was this gap between the simulation and the real world, right? Because getting a real fleet of self-driving cars to drive around in town is very complicated for a number of reasons and very expensive. So we built Duckietown to be some sort of experimental simulator to factor in the challenges that were of course, in the real world, without having to have millions of dollars and convince legislators, of course. So it began with this graduate level master degree set of pedagogical materials and learning experiences. And the idea being that all the staff and the students that were participating in the first editions of the course, as part of the course itself, they would get in groups, make projects, and each one would be developing a different aspect of the whole autonomy pipeline. So from the team of students that did the link following to the ones that did the LED recognition, the coordination mechanisms, and all of that. And all these pieces of code ended up being part of a single, let's say, corpus that was shared with the broader community. The whole code is open source. You can go on GitHub and you will find the Duckietown GitHub repositories. And the idea being that thanks to this initial push of the more, let's say, expert students and contribution from the broader community, then we could go back and provide these learning experiences not only to the graduate level classes, but to the undergrads, which is something that has been going on in the last years, and eventually even to high school and to even younger folks. Duckietown is designed, as we'll see later, to be a single platform with scalable complexity that can go from literally 0 to scientist level. Duckietown enjoys a large international community, people from all over the world, from robot clubs to universities, to high schools in the middle, to museums, use Duckietown to do research, to do teaching, and to do outreach, to really stimulate the curiosity of the broader demographics and into what is robotics, what is AI, how does it work? Is it really out there to steal my job, you know? And substantially what Duckietown offers is a step-by-step guide to state-of-the-art autonomy. So we have this rich corpus of documentations or documentation. You can find it online. And it's a kind of a Wikipedia system. Anybody can contribute and debug information, add more, let's say, autonomous behaviors or different applications. And the most tangible part of the platform is, of course, the whole hardware part. The idea is imagining walking in a room and having an ecosystem, which has of course, the self-driving cars, fleets of these self-driving cars roaming around in this big modular urban environment that seems colorful and toyish, but it's actually structurally specified. So all the dimensions, the colors, the let's say, infrastructure that we mount on top of this city is all specified to satisfy a number of criteria that the robots will assume in order to carry on their autonomous behaviors. And we have a parallel drone initiative as well, which is led by Professor Stephanie Telix at Brown University, which is more targeted towards the high school. We already did a number of pilots in Rhode Island schools, and shortly we will be bringing everything together, creating this land, air, and smart city environment where autonomy is obtained with a focus on computer vision, although there are a number of other sensors on the various different robots. And the whole system is really created in a way that behaviors of different complexity can be easily scaled. On the software side of things, the whole Duckietown system is built using let's say, common tools that are today used for doing robotics and AI. So we have Docker, we use Python, ROS, GitHub, and of course there is let's say, a backend user experience glue. That is what Duckietown provides to really make it easy to pass between the theory, which is the various slides and exercises, and let's say operation manuals are provided, to actually implement into both the simulated world of Duckietown as well as on the hardware. So we put really lots of work to standardize the interfaces and make it as easy as typing 3 lines of code to, for example, train a machine learning solution on either real data from the robots or from our simulator that is designed on purpose to do learning, or from, for example, a database of logs of other robots around the world. And with another line of code, we can then evaluate let's say, the performance of this agent that is designed either in simulation or on hardware, both locally or in remote facilities. We call them the auto labs, which are nothing but the big cities you saw before. There are smart Duckietowns that are able to localize the various robots and therefore track the paths and create all sorts of performance metrics out of the specific tasks that the agents are trying to solve. And of course, the whole platform is open source. As we're carry on and producing this MOOC, we will have a nice sequence of classes paired up with software implementations and deployment on the real hardware. And the whole platform, as I mentioned, is modular. So it's extremely easy to switch a block and for example, change the controller or change the planner or change whatever filter you're running to maybe detect the lines or other duckies or other cars, and test either variations of solutions that come from textbook solutions, let's say, or actually do research. So in a very reproducible fashion, because by standardizing all the interfaces and using Docker, we basically managed to freeze all the headaches that Dustin was mentioning earlier, all the dependencies, all the various bells and whistles that are necessary to really make a code reproducible in time. What can Duckiebots do? Well, they pretty much do what you would expect from a self-driving car. So what we're seeing here is maybe one of the simplest, the standard lane following image pipeline. So we have, this is of course running in a decentralized way. So all sensing, decision-making, planning is being done on board. And we see the images coming in, we see the various pre-processing being done, the rectification, the color correction, some feature extraction. So in this case, we see the edge detection of the various lines in the lane. And then by leveraging, of course, a mathematical model of what the city should look like and data from the calibration from the camera, robots are able to reproject recreate basically a 3D image, actually it's a 2D image of the world around them and localize in real time in it by using recursive Bayesian filter that is implemented in a discretized way through this histogram filter that you see there in the top right. And of course, being the platform decentralized, this means that this is running on every robot and there's no limit to how many robots you can put. There's no eye in the sky, there's no super server. And so there's lots of multi-robot behaviors that can be developed from coordination at intersections. So trying not to let's say, to yield to the robots, other robots at the same intersection, trying not to crash, or from doing planning or obstacle avoidance or formation control. So trying traffic management, let's say. There are many, many possibilities that arise from having this modular ecosystem. Duckietown is used for education and research. So in the teaching domain, we have developed our Duckietown courses of different level, let's say, of complexity, from a more hands-on, let's say, introduction to robotics that stresses more the, let's say, operational and let's say setup and execution part of the whole discipline to more advanced autonomous behaviors, and of course all the machine learning more recent applications. But Duckietown has been used a lot even as a support for traditional courses. For example, when I used to teach control systems, I used to have students implement the controllers on various Duckiebots, and so it's possible to basically hide under the hood, let's say, all much of the let's say complexity that maybe is unnecessary for students at the earlier undergrad level doing specific courses, and really make them play only with what is of interest to them. The Duckietown courses are designed to really be hands-on, of course. The whole idea was to create a platform where people could, where students could get together and see the theory working or not, often not in practice, and get together to build a complex platform that demonstrated non-trivial autonomous behaviors. So we have this project-based, of course, structure. We have step-by-step, let's say, instructionals and operation manuals and exercises and a number of pedagogical materials that are that have been developed in the last 4 years to address the various skills that are more required and by different students. And when I say this is because when we teach Duckietown in different universities, in different departments. So maybe you have the computer science departments where the students are maybe weaker on the control system side, for example, of things. Or when we teach Duckietown at DTH, we have mechanical engineering department, so students maybe have never coded or have very little experience with ROS, with Python, or let alone with machine learning approaches. So it is easy to adapt the whole system in order to highlight or not the various aspects of the autonomy pipeline. Research-wise, let's say a cheesy statement of Duckietown is that with a fraction, of course, of the cost of a real self-driving car, one can get a significant part of the scientific value of it. So the scientific challenges behind autonomous driving, the perception domain in particular, can be captured by this small little low-cost open source platform that uses only a camera and has such constrained computational resources on board that this was at the very beginning. Now, of course, with great new additions to the Jetson family, we have much more horsepower on board, and we can start doing way more fun stuff. The modularity of the system allows, of course, to easily move between more traditional approaches to autonomy, let's say planning, perception, and control, see, plan and act kind of philosophy to just using combinations of machine learning based solutions, from end-to-end learning from the observations of various sensors on board to the commands to the wheels, or maybe just in, for example, learning how to adapt to external disturbances, such as variations of lights in the room and things like this. A application, as I was mentioning before, of the whole Duckietown platform is the AI Driving Olympics. The crux of it being trying to understand how much this embodied AI research is proceeding and how to actually benchmark it with respect to traditional solutions. So the idea is that anybody around the world can either with hardware or without, so just by using simulation, start from some baselines that we provide in different learning approaches, reinforcement learning, imitation learning, train their algorithms and create agents that then they submit to our challenges server, which is basically a cloud evaluator that tests these agents in a multitude of different scenarios in a series of challenges of increasing complexity. So we go from the, let's say, easiest, the lane following a robot alone in a city without intersections. And then we can start moving across different dimensions of complexity. For example, making the topography of the city more complex by adding intersections or traffic signs or maybe traffic lights, or by instead keeping the city simple, so just a road loop, but adding other agents, so other robots that might be controlled by they might be non-playing characters, so running, let's say, baselines that we provide, or running agents that are provided by the competitors themselves. So we have multi-body challenges as well as, let's say, other challenges where only one robot is controlled by the users. And here it's all about understanding how well does this process of, for example, sim to real learning work? Can we train in simulation and then apply the results in the real world, or to what degree, and how well does it work? And we can actually quantify all of this pretty rigorously thanks to the infrastructure we make. So what I'm trying to maybe convince you about or stress is that we created this whole platform for a number of reasons. And first one is that it's not just only about the teaching, the research, and the outreach. It's really about the intersection of all of this. It's a non-zero-sum game. So you really can get nonlinear benefits by having a single platform that you can use to do your research in the lab. So train the PhD students, or maybe have master students that are doing their master theses and applying different state-of-the-art solutions to Duckietown, and have this the same platform being used for teaching, and then for maybe doing scientific fairs, attracting, let's say, people who don't have a background in this thing, and having the students themselves reach out to them and explain and do dissemination in the process. Duckietown, thanks to the fun, let's say, presence of the Ducky and the colorful environment, is literally one of the few labs that has people outside watching even when the lights are off and nothing is going on. It really attracts the attention of who would not otherwise be already passionate about the robotics. So it's really a way to get the attention of students. Another key idea is that of unity. We have a single platform that is designed to be sufficiently flexible to go from 0 to literally research level. In the last 4 years, since Duckietown was created, I think 120 something papers were written either by using Duckietown or citing Duckietown or talking about Duckietown in one way or the other. Then there's this key idea of standardization. We know that the hardware is an important part, but we really believe that the deployment of the software architectures is what is the frontier of autonomy. So we designed the whole thing in order to take away the headaches of having to get the hardware to work, but really provide the hardware to each and every student or to each and every researcher in a way that's scalable. The whole platform is very low cost, very affordable. And we use software solutions that are the software solutions that are used out there. So the students, once they learn on Duckietown, they can easily transfer their skills to other projects, or maybe to the workplace once they proceed with from their studies to joining the workforce. Another key idea of Duckietown is this of the modularity. We do provide, of course, initial solutions for participating in the IDO. So let's start starting to do research. But really, the whole thing is open. It's 100% open. There is no black box doing magic. So anybody can create their new classes, can apply their research, can contribute back to the whole system if this is what they desire to do. So it's very flexible. It's very versatile platform. So this all comes together in the Class in a Box, that is a one-click solution for learning autonomy. So when I say learning, is because we both, when we do research, we learn. When we teach, the students learn, but everybody's learning at the end of the day. So, and it's fundamentally a very convenient and easy way to get a complete hardware ecosystem, to get all the pedagogical materials from the slides, the exercises, the operation manuals, to get access to all this infrastructure that we use for the driving Olympics. So the ability to have your students submit agents, so solutions to autonomy, to our various challenges, and basically get automatically graded, if you want, not graded, but evaluated. And of course, we provided the community. There's a very active community. We have Slacks both for only students and for only instructors. And there is a lively environment where people help each other, launch research projects or whatnot. And there's lots of international collaborations at different levels. So this said, I hope I have not taken too much time. Thank you for your attention, and would be happy to get questions if you have. I see there is actually a list of questions already.
All right, thanks, Jacopo. Really appreciate it. So if you guys have any questions from the audience, type them in now. We'll stick around for a few more minutes to take some questions. There was one here about they said that they teach ROS in their department, and which versions of ROS can you run? So on the Jetson, it runs Ubuntu, and folks are running ROS Melodic or the newer ROS Noetic. But really, we see a bigger migration to ROS 2 now that that's been coming out more and more. And NVIDIA is actually on the ROS 2 working group, and we made a bunch of contributions to that. So you can even do, I think it's ROS 2 Eloquent and Foxy are other versions. So you can run all your normal versions of ROS in the nodes, and um, people frequently like to take the SLAM and mapping nodes like RTAP map or G mapping and run those right on the Jetson, which can take quite a bit of horsepower. There was one here about how do I run simulations on the Jetson, or what's your simulation strategy? So we have seen folks like do the simulator directly on Jetson because that has that GPU and graphics. So they'll run like the ROS Gazebo simulator, or I think I've even seen Unity being run right there on ROS. And a lot of those race car courses, the RC cars we mentioned earlier, those have simulators to them. Jacopo, do you guys have a simulator for Duckietown? I saw in that one
Yes, I
animation.
see a question. I was actually trying to find the link so to address it specifically. But yes, we do have a simulation environment. If you go on challenges.duckietown.org, you will see it working in action. So where we use this whole simulation environment to create the various challenges, all sorts of different maps, all sorts of different environments, so more or less cars, different kind of assets in the map, and you can see how things perform and a lot of engineering data coming out of it.
Cool.
I'll find the link and send it out to you.
And then on the higher end, there are obviously a whole bunch of simulators you can run in the cloud, and NVIDIA has a robust one called the Isaac Sim, and it's based on like the ray tracing technology in the latest cards. So you can fire up a cloud instance and run these really high-end simulators there as well. But there are ones that the students can run directly on their Jetsons if they want. I see a question here. What prerequisites do you recommend that the students have? I'll let Jacopo answer for his end in a second, but on our side, generally they can come into this with basically no CS knowledge. It is nice to have some familiarity with Linux or Ubuntu and know your way around the command line a little bit, or know some Python. But a lot of like the trainings that we had seen from the AI certification program, you basically don't need coding knowledge for that. You can absorb a lot of Python through it, but some Python background is nice to have. What about you, Jacopo, with Duckietown?
So in the Duckietown courses are more tailored for master level and let's say university level. So we do recommend that people that walk in have at least some experience of programming in some language. We do hope that they have some familiarity with terminal usage, maybe installing Ubuntu, not using Windows, basically. It does help to have some basics of maybe kinematics, dynamics, having some linear algebra basics, knowing what a matrix is, knowing how to do matrix operations. Some probability might help because there is this. I mean, it depends, of course, at the level at which you want to see it, but some math background, some physics background, and some programming experience with any language, then things can be picked up as you go.
Great. Okay. Question came in. What can I run on the Nano 2 GB versus the 4 GB? Because obviously, the 2 GB is less expensive at only $59, but only has 2 GB of memory versus the 4. So all of the stuff that we showed, all the tutorials and certification courses, those all run on the 2 GB. You can train models and do object detection and segmentation all on the Nano 2 GB. So we've actually been pleasantly surprised at the amount of models and such that you're able to run on that all simultaneously. And later, I guess I had meant to put up a closing slide here with our emails on it. But if you are interested in hardware seeding grants or want to teach a course or something, go to this link here, or Jacopo and my email is shown here. So feel free to reach out and get in touch with us. So we have some units earmarked that can go out to professors that want to teach courses and do this stuff, so you can apply for hardware seeding for those units. And also shown here, we have this developer blog we launched recently. There's an interview with a bunch of the initial folks that took this AI certification program. So if you're interested on feedback from the community, what they thought of it, check that out, and you can see some, direct from the horse's mouth of people that have actually gone through it. So yeah, I encourage you to look into it and maybe prompt some of your students to get certified as well. So with that, we're already a little bit over the hour. Sorry about that. But if you have any follow-up questions or want to collaborate, feel free to email us directly. We're always available.
All right. Well, it looks like it's time for us to wrap up this webinar. Thank you again to Dustin and Jacopo, and thanks everyone for joining us. On behalf of ACETA, I'd like to thank NVIDIA and Duckietown for making this ECE webinar possible. Thanks again, and have a great day.